Okay, in this lesson, we're looking at matrix multiplication. So rather than scalar multiplication, where we're multiplying a matrix by a real number, we're instead multiplying a matrix by another matrix. This is also called row by column matrix. And for the first little while, you're going to have that sensation of having swallowed that red pill. And hopefully, once it works its way through your system, you feel better about that. So I'm going to start with just by doing an example. And as I do that example, I'll talk through the steps. And then you'll notice at the bottom of each screenshot, there's a couple of sentences in red. And those are really the instructions or the key tips to remember as you're doing matrix multiplication. So I'm multiplying these two matrices that are both 2 by 2. I'm going to multiply them together, and I'm just going to talk you through the steps that I'm taking in order to do that. So the first thing I'm going to do is use row 1 and column 1, and I take the first element of each and I multiply them, so that's 0 times 6. And then I take the second column of second number of each, and that'll be a 2 times 3. And I add those together, so that'll be 0 plus 6 gives me 6. Then I'm going to take that top row, and I'm going to work with the next column. So that's 0 times negative 6 and 2 times 1, which gives me a 2. Now I'm ready to move to the second row, and I'll just switch colors here. So I'm looking now at the second row, and I'm going to go back to the first column. So I have negative 2 times 6 for negative 12, and negative 5 times 3 for negative 15, and add those together, and I end up with negative 27. And now I'm still on the bottom row, the second row, and I'm going to move to the second column. So I have negative 2 times negative 6 for positive 12, and a negative 5, which gives me 7. And that is those two matrices multiplied together. So if we scroll down here, we see these two steps. I'm using the rows of the first and the columns of the second. And what I'm doing with them is first number times first number plus second number times second number, etc. And depending on the size of the matrices, I might have to continue doing that. Okay, so it's first times first plus second times second, and it's the rows of the first one with the columns of the second one. In that first example, both of those matrices had the same dimensions, but multiplying matrices can work also if the two matrices have different dimensions. So in this example, I have the first example is a 2 by 1 matrix, also called a column matrix because it consists of only one column, and I'm multiplying it by a 1 by 2 matrix, which is a row matrix. It's got just the one row. So I'm going to follow the same steps here. I'm going to start with the first row, which is just this one number, and I'm going to put it with the first column, which again is just one number. So that's 6 times negative 5 gives me negative 30. I'm going to stay in the top row until I've dealt with all of the columns of the second one. So that gives me 6 times 4 for 24. Now I'm ready to move down to the second row. So I have negative 3 times negative 5 is positive 15, and negative 3 times 4 is negative 12. Okay, so notice that here I needed, because I'm dealing with the rows of the first, which means I need to have the same number of columns in the first one as I did rows in the second one. Okay, so that's one of the key things, the key learnings here, is that the number of columns of the first matrix has to equal the rows of the second. Otherwise, you end up with one of your multiplications having more elements than the other. So it's not just that they are equal, but they must be equal. Okay? And your product will have the rows of the first and the columns of the second. So the product, the dimensions of the product are not necessarily the same as the matrices that you started with. In example 1, the product was the same size as the original ones, and in the second example, the dimensions are different from the original ones. So we're going to look at next, how can we figure that out? Okay, so, and there's so much talk of rows and columns, so it's easier to illustrate it this way. If I look at example 1, I had the first matrix was 2 by 2, and the second one was also 2 by 2. In order for me to be able to multiply those two matrices together, the columns of the first and the rows of the second must be equal. The resulting matrix, or the product, will have the dimensions of the rows of the first and the columns of the second. So my product of those first two is a 2 by 2. And because they were square matrices, it ended up that they were all 2 by 2s. If you look at the second example, the original matrix, the first one was a 2 by 1, and the second one was a 1 by 2 matrix. Okay, so the one column of the first matched the one row of the second one, and our product had these dimensions, 2 by 2 product. Okay, this is very helpful, and in fact I would say it's mandatory. You want to always do this check first before you actually multiply matrices. Know what size your product is going to be. Okay, so let's look at a couple of examples where we do that so that we can determine what happens. So here's a question. If matrix A is a 2 by 5 matrix and matrix B is a 5 by 3 matrix, what are the dimensions of A times B? And then we'll also look at what happens if I reverse my multiplication and do B times A. So let's do the first one where we have A and B. So put in order, write out their dimensions. So A is a 2 by 5 and B is a 5 by 3. Okay, the columns of A match the columns of B. They're equal to each other, so that's good. Our product will be a 2 by 3. Okay, now what happens if we try to reverse that? When we reverse numbers and multiply, we get the same product. This is not true for matrices. So if I wanted to have B first, that would be a 5 by 3, and A is a 2 by 5. Notice that the columns of B do not match the rows of A. They're not equal, so actually the product is undefined. We cannot multiply those together. We can only multiply matrices where the columns of the first one are equal to the rows of the second one. So two good reasons for doing this dimensions check first of all, and the first reason is illustrated up here, whereby we end up knowing what our matrix product dimensions will be. It's very helpful for figuring out the number of spaces that you're going to have to fill in doing that multiplication and addition. And the second reason is actually illustrated well here, because some matrix multiplications are undefined, and so you cannot actually even start trying to multiply them. So now let's try an example. Here's a first example, and for those of you who are feeling a little bit confident, you might want to press pause now and try the multiplication first yourself, or even just try the dimension check first yourself, and then hit play again to check if you've done it correctly. So let's do the dimensions check first. The first matrix here is 3 by 2, and the second one is 2 by 2. Notice that our columns and rows match here. which is good, which means we can multiply. And our product is going to be a 3 by 2. Okay, so that means that I can then now space out a 3 by 2 matrix for my solution. So I'm going to start with, I always start in the top left corner. So I'm going to start here, and this in my product matrix, in my answer here, this is row 1, column 1. So row 1, column 1 tells me that the answer that goes in this location comes from row 1 and column 1 when I'm multiplying. Okay, so I've got 0 times negative 4 plus 5 times negative 2, and the answer is 10. Now, it's a 3 by 2, so I'm going to have two columns, so I'm going to just move across, and I'm going to do this result now. This is row 1, column 2, so I go back to my question and use row 1 and column 2. So 0 times 4 plus 5 times negative 4, so that gives me a negative 20. Now I'm moving down to row 2 in my response or my product here. So I'm going to move down to row 2 here, and I'm going to do row 2 and column 1. So there's positive 12 minus 2 for 10. And I'll move to column 2 now with the same row. I've got negative 12 minus 4 minus 16. Now I'm ready to do row 3. We'll do that one in black. So row 3 with column 1 is positive 20 minus 2 gives me 18. And with column 2, I've got negative 20 minus 4, negative 24. And there's my solution, or my product of those two matrices. So if we scroll down here, we'll see the tip from this question. In the product matrix, the element in row 1, column 1 is produced from row 1 in the first and column 1 in the second. And another example would be the answer in, for instance, row 3, column 2 comes from multiplying row 3 in the first and column 2 in the second. So the position in the product is represented by the rows and columns of the two matrices that you're multiplying together. And one more example to look at, and again, you might want to press pause and do your dimension check and even try to multiply these yourself first. So when I look at the dimensions of these two matrices, I want to see if the product is defined. Matrix A here is 2 by 3, and matrix B is a 3 by 2. So I can see that we match here, so the product is defined, and our product or our solution will be a 2 by 2. So now we're ready to move forward. So I can set this up. I'm going to have a 2 by 2 response. So row 1, column 1 will come from row 1 and column 1. So I've got negative 20 minus 9 plus 15. I think that's negative 14. Now I'll go to column 2. So I've got 10 plus 12 minus 25, so negative 3. And now I'm ready to move to row 2, and I'll do the column 1 first. So I've got negative 4, negative 15, plus 0 for negative 19. And then I've got 2 plus 20 plus 0 for 22. And done. So practice, as you practice these questions, always do this dimension check first, and it will help you to ensure that you're getting the correct product when you multiply. It does take practice to get good at this, and in the classroom I'll show you what I do with my fingers as I'm multiplying so that you can see. It is like patting your head and rubbing your tummy, but you can see the steps uh, the visual and sort of the kinesthetic steps that I go through in order to get the solution matrix.